Have you ever stopped to wonder what's physically happening inside a machine when an AI thinks? I mean, it's not just magic floating around in a cloud, right? It's a real physical journey. And today, we're going to follow a single request from you, the user, and trace its path from a hard drive through these intricate silicon pathways and watch as it becomes a flash of artificial insight. Let's dive in.
So, when you type a question into an AI, where is that thought actually taking place? It's not in some abstract digital void. No, it's a physical relay race happening at almost the speed of light inside a very real machine. We're going to follow that race step by step to really see how it all works under the hood.
So here's our roadmap for this journey. First up, we'll meet the hardware, the key players. Then we'll see how a model is actually forged during training. After that, we'll uncover a really critical memory bottleneck, witness the actual spark of a thought during inference, and then visit a special library that makes conversation possible. And finally, we'll take a peek into the future of AI hardware.
Okay, first up, the hardware stage. Now, you should think of this less like a single computer chip and more like an entire orchestra. Each section has a very different role, and they all have to play together in perfect time for the magic to actually happen. This right here is the physical journey. Your request starts out on a solid-state drive. That's the long-term storage. From there, it gets loaded into the system's main memory, or RAM. Then the computer's brain, the CPU, basically acts as a traffic controller, sending that data over to the real star of our show, the GPU. But even inside the GPU, there's a VIP section. The data moves from the GPU's main VRAM into its ultra-fast on-chip caches, called SRAM, literally moments before the calculation happens. With every single step, the data gets closer to the core, and the speed just ramps up exponentially.
And this chart, wow, this really shows you why that journey matters so much. Just look at these bars. Your system RAM is fast, sure, but the GPU's high bandwidth memory, or HBM, is over 10 times faster. And then you get to the on-chip SRAM, and the speed jumps another tenfold. This incredible speed hierarchy is the single most important concept in all of AI hardware design. It's all about one thing. Proximity to the processor is everything.
All right, now let's talk about training. If getting an answer from an AI is like visiting a library, well then training is the massive, incredibly energy-intensive factory that had to build that entire library in the first place.
The process of training has this fundamental heartbeat to it. First, in what's called the forward pass, the model takes a guess. Then, in the backward pass, it calculates how wrong that guess was. And these errors have a name. They're called gradients. Finally, in the optimizer step, it uses those errors to slightly adjust its internal wiring, its parameters, to make a better guess next time. And this simple three-step loop is repeated trillions of times to forge the final model.
So here's a little puzzle for you. A model like Llama 8B might have parameters that take up, say, about 16 gigabytes of space, but you can't train it on a GPU that has 32 gigabytes of memory. So why does training require so much more room? It seems like it should fit, right? Where did all that extra memory go?
Well, the answer is pretty surprising. During training, every single one of those billions of parameters needs more than just its own storage space. It needs room for that error signal, the gradient. And most importantly, it needs space for the optimizer's own notes, kind of like scratch paper for learning. These optimizer states are absolute memory hogs, and with common tools, this can swell the memory requirement to 18 bytes for every single parameter in the model.
And as you can see in this breakdown, which was inspired by the groundbreaking Zero paper, the model's actual parameters are often the smallest slice of the pie chart. It's those optimizer states, that learning scratchpad, that just devour the most VRAM. They're just like the scaffolding needed to build a skyscraper, absolutely essential for construction, but they take up a ton of space and are totally removed once the building is complete.
This intense memory pressure forces a really critical trade-off. You can try to keep everything on the GPU's ultra-fast VRAM, but you're going to be limited to smaller models. Or you can offload the bulkiest parts, like those optimizer states, to the much larger but much slower system RAM. This is the whole strategy used by systems like DeepSpeed Zero, and it's a key reason why architectures like Apple's unified memory are so interesting. Okay, so our factory has finished its work and the model is finally built. Now it's time to switch gears completely and talk about inference. This isn't the factory anymore. Now we're in a high-speed, futuristic library, and our only goal is to find one specific answer as fast as humanly or inhumanly possible. Getting an answer actually happens in two distinct phases. First is the prefill phase.
This is where the model absorbs your entire prompt all at once in one massive parallel calculation. This part is all about raw computing power. But then comes the decode phase. This is where it generates the response one word or token at a time. And this part isn't limited by computation at all. It is a pure race to see how fast the GPU can read its own memory.
And this is really the key takeaway for AI speed. When you're sitting there watching that cursor blink, waiting for the next word to appear, the bottleneck isn't how fast the GPU can do math, it's memory bandwidth. The true speed limit is how fast that chip can pull the next piece of information from its own memory.
So, if memory speed is the real limit, how do we make every single memory access count? Well, that question leads us to the secret weapon of modern AI, a really elegant optimization that basically acts as the model's short-term memory.
It's called the key value cache, or just KV cache. Every single time the model thinks about the conversation history to generate a new word, it saves those intermediate calculations, the attention states, in this special cache. What that means is it doesn't have to reread and reprocess everything you've said from the very beginning for every single new word it writes. It's the reason chatbots can maintain a long, coherent conversation without grinding to a complete halt.
And the evolution of managing this cache has just been breathtakingly fast. I mean, it started with these simple but really wasteful methods that pre-allocated huge chunks of memory. Then came these amazing breakthroughs like page detention from VLM, which cleverly borrowed memory management ideas from operating systems. Now, we're in an era of managing multiple complex caches at once, and we're heading towards systems that can manage a single distributed cache across an entire data center. It's wild.
So let's just recap the entire journey. The full model lives on relatively slow storage. During training, data is constantly juggled between system RAM and the GPU. But for inference, the real action, the model parameters, and that critical KV cache lives in the GPU's superfast VRAM. And then, for the calculation, at the exact moment it happens, the data makes its final jump to the Lightspeed on-chip SRAM. It's a constant, complex dance across this entire memory hierarchy.
So where does all this leave us? Well, the physical limits and the incredible speeds of hardware are constantly shaping what AI can even do. And looking ahead, the focus is shifting in some really fascinating ways.
You know, we're seeing three huge trends emerge from all this. First is quantization, which is really just a fancy word for making the numbers smaller. By reducing their precision, we can literally slash memory usage and boost speed. Second, we've got unified memory architectures, which are erasing that strict line between system RAM and GPU VRAM, making it way easier to work with enormous models. And third, these new algorithms, like the famous flash attention, are being designed specifically to minimize those slow trips across the memory hierarchy, keeping all the action on that super-fast on-chip SRAM.
All of this leaves us with a fascinating final thought. For decades, we measured a computer's power by its raw computational speed, its flops. But as we've just seen, for modern AI, the true bottleneck is increasingly memory. It's not about how fast you can think, but how fast you can remember. The fundamental challenge is shifting from calculation to recollection, a challenge that is as true for our silicon brains as it is for our own.